I'm on it with you. And yeah, if you're having trouble with Summary 3, use the forum. That's what it's for.
Ask questions.
There's a forum. Just throw it out there. Peer-to-peer learning.
Don't submit your assignment there. Just.
Oh, no, that's what it's for. That's what the forum is for. Okay, so here's a neat evolution of reactor startups, and each one of these here's 1, here's 2 or 3, there's 5, there's 4. These are discrete events in time. First shutdown started in the mid-60s. Peak startup was in the 80s, and gosh, you can see here haven't been too many nuclear startups in the last several years, and where exactly that'll go, I don't know. I do know that China has some plans to fire it up.
Has there been any between 2009 and 2006?
I'm sure there have. I don't know all the history on it, but there's a growing interest in these smaller thorium reactors, and I think we are going to see.
A little spike.
Yeah, and I think we're also going to see energy become more distributed.
Well,
Even solar panels on the roof is a good example.
There's cleaner coal plants too that China's working on building.
Yeah.
To get that are more efficient.
Yeah. So we'll see another
The
surge.
thorium reactor, that small reactor the kid built in his garage?
Maybe. I know a lot. I think there were debates, back in the 60s about whether we would use uranium or thorium, and there were arguments for thorium.
I've never
And
heard of thorium.
yeah, it's right there, radioactive in the periodic table, and it could be that's kid built one in his backyard.
Yeah, some
Hope he was-
genius, a
hope he was
14-year-old,
protected.
15-year-old kid built a small nuclear reactor in his parents' garage, and whoever found it,
Yeah.
now apparently they're working on it.
Yeah,
That's cool.
Yeah.
That's wow.
Like they would fit in the size, like basically like they would go in people's backyards.
yeah.
Jesus. Wow, that's creepy.
So let's look at the physics here of nuclear energy. I'm going to pull up uranium on the dynamic periodic table. Let's take a look at it. One thing to kind of center yourself on this is iron. So anything lighter than iron, anything with fewer than 26 protons, is undergoing fusion in the sun. So in the sun, hydrogen fuses to form helium. As we sort of work our way up the periodic table, once you hit iron, fusion tends to stop. But so on the other side, and let's see if we can find uranium. I think it's number 92. Right? Yeah, there it is, uranium 92. These larger nuclei are less stable because there's so many protons jammed in one place. And you'll also notice, if you multiply 92 by 2, you get 184, but the mass of the uranium atom is much larger than double. So it takes more than double the neutrons in the nucleus to shield those protons from each other.
It's more layering or whatever.
Yeah, and so it's uranium-235. Notice it's not uranium-238. It's uranium-235, which is the radioactive. It's the good stuff. No, 235 is the fuel.
Oh, okay.
235 is the fuel because it is less stable than the heavier isotopes of uranium.
So thorium's right next to that.
Thorium's right next to it. Yep.
I've never even heard of that.
Well, it's because the government doesn't want you to, Matt. So we know you'll start building thorium reactors in your in your garage, and you'll put Northwestern Energy out of business. So that's why you've never heard of it.
Right?
Yeah.
Conspiracy.
Okay. And here's plutonium. That's also that can also be a byproduct, and plutonium is not a naturally occurring element on planet Earth. It's a byproduct. It's manufactured in breeder reactors, and we'll look at some of those reactions here.
Are those
Probably
the
not today.
rods or
But,
whatever?
beg your pardon?
Are those the rods?
Uranium is in the rods, and we'll look at that momentarily as well. Yeah. So what's going on with radiation You can see, we just talked about neutrons. That's exactly what this is. This neutron can pass right through paper. There's nothing really for it to stick to, right? It's not charged. It's just going to say, hey, see you later, right through aluminum, right through lead. It's not until you get a whole lot of concrete in one place that the neutron tends to find a home. Here's the gamma radiation. That is a high energy photon. So you could call it light. It's not really light. It's much higher frequency, much higher energy than light. Remember we did that little calculation where we looked at the number of joules in a single light.
Like a cubic meter.
Yeah, we did the cubic meter, but we also said there's something like 10 to the minus 19th joules per photon. These photons have higher energy.
And they're super harmful, aren't they?
Oh yeah, they'll go and knock out your DNA. They'll go in and mutate your DNA for you. Yeah,
Oh, wow.
yeah.
Okay, I didn't know.
So they'll go right through paper, right through aluminum, but they'll get hung up in lead. Beta particle, that's an electron. That's actually so the neutron has mass, the photon does not. The beta is a highly charged electron, blasts right through the paper, but gets some aluminum from it, it'll get stuck in there. The alpha,
Looking at them.
the alpha is this is an alpha particle right here. It's bigger, it's bulkier. It's
Just a discharge?
it's more or less a helium. It's more or less a helium atom, helium nucleus just flying right out of there. So there's alpha, so-called alpha decay. Two protons and two
So it's not
neutrons.
like, we're not talking half-lives here, we're talking just decay rates? Are they different?
We'll talk half-lives in a second.
Okay.
We haven't even talked about rates at all.
Okay.
All we're looking at is the physics of what's going on
Okay.
down at that
I guess
scale.
I was just-
Yeah.
So with the gamma rays hitting the lead, that's where it becomes dangerous for humans.
Well, all those are showing is like the penetrating powers of different types of radiation.
Yeah, but with the gamma rays hitting the lead, I mean, that's like the rods, right?
Mm-hmm.
Okay.
Yeah, we'll look at the mechanics of the reaction here in a second. But and the gamma rays themselves, may or may not contribute to the reaction. But the gamma ray, if it comes in and can't remember all the details, but it'll come in and bind with one of the nucleic acids and mutate it from like an A to a T or a G to a C in your DNA, and then
Wow.
you're fundamentally
Different.
changed.
Yeah.
And there's a lot of early, like a lot of evolutionary biologists will look at that as a way that just a mechanism for driving evolution,
Trippy.
mutation. Yeah. Mutants. Okay, so here's an example. This is radon.
That's in all over everyone's basements up in the South
Yep.
Dakota.
Yep. This is why you really don't want radon in your basement. It is radioactive. Here's polonium, and you can see when that alpha particle blasts out of radon, the atom itself turns to polonium. There it is, taken off. And we can just do the math here. So radon has 86 protons. Its nucleus, helium has 2. 86 minus 2 is 84. This particular isotope of radon had 222 total. So 222 minus 86 neutrons. Nuclear particles, so protons plus neutrons. Subtract the 2 protons and the 2 neutrons. 222 becomes 218 polonium. All right. Here's a beta coming off. This is iodine. Fukushima. I'm going to check out the Fukushima iodine movie. I love that thing.
Isn't, like, I've been hearing about how it's been missing more, like, they've been finding out how it's affecting more and more of the Pacific than they originally thought.
I know.
getting in the fish and
Yeah.
reaching the California coast now or something like that?
Well, there was a big, I misspelled Fukushima. It's this one. It's this one. So here's the plume, there's the pan, and this is just iodine. It's just normal weather patterns causing this, and that has it, that was just the blast. And not know exactly what the units are, but this is why Fukushima spilled in 2011. I can't really see the date, but down here we're also sort of clicking off. These are maybe in the order of hours. It might take place over the course of a week or two. That's why people in California were going out and buying a lot of iodine to put in their bodies, because if you have radioactive iodine in your body, again, it goes into the message yourself. So this is just one example of what happens when iodine pays into xenon. Let's look at that. Xenon being more stable, at least in that form. So well, that's the second law of work. Just things become more absorbed. Everything kind of ends up everywhere. Who do you hold accountable? What do you do, Ro? What do you? No, I mean, sure, they are. It's a windy problem. I actually met the lead engineer who's on staff at Kanagawa when it went down, and he had to stay at the plant, make sure nothing worse happened while his family drowned. From the tsunami. It was real, it was scary. So that was back to the periodic table though. Let's look at the from that iodine. Here, xenon. So this is kind of wild. This electron, when this electron leaves, and this is kind of a strange, interesting quirk of nuclear physics, the total mass of the atom did not change. It's still 131. It's iodine 131. We know an electron has mass. It just took off, but its mass is the same, give or take. Granted, we're only looking at 3 significant digits here. 131. So there's probably some noise out here, but the proton turned into a neutron. Let's just look at that.
Number 12 is the BBC News recently reported radiation levels around Fukushima are 18 times higher than previously believed.
Equals 1.
And, again, it's TEPCO's numbers,
that's
which
the
are
math
always
we do.
revised higher.
Put a proton together.
With the last few weeks where we've had
Put an
kind of this
electron together.
escalation of
Put the
events, one of
proton
the
with the
things that I
electron.
found really curious is that because of
And a neutron is
wall that was built underground to block the corium from going out
Neutron.
into the sea or highly contaminated water going
This
out
has a
into the
mass of
sea.
approximately 1,
Effectively,
this has a
they've
mass of
dammed up the
approximately
site
0, and this
so
has a
that the
mass-
ground is now
mass of
becoming
approximately 1.
saturated. And if you have this underground, corium lava field, under the reactors, you have groundwater that's flowing through the site, and you have water that's continuously being poured on the
We'll do one
reactors.
more
They're
little
only
bit of math
collecting 300 or
together,
400 tons of that a
and
day.
then we'll do summary together.
I think what we're going to see eventually
All
is
right,
that
so we've already done some
this
units conversion today.
corium
We did
groundwater combination is going to
energy
be
to
coming up around
energy.
the site, and at that
Now we're gonna
point,
do
workers aren't going to be able to be there.
energy to mass. And we get
There's no way to
invoke
protect them,
Einstein.
especially from tritium, because tritium will go through
So,
everything.
1U,
So, you know, they're really
One
under
U,
the
and I
gun
already
for anything
alluded
that they
to
need
that.
to do, and, you know, they're going to cycle through workers
1U.
continuously. There's no way to keep people
proton
on the
has
site
a
for
mass
long
of
term with the kind of
approximately 1U.
exposures they're
An
getting
electron has a
with
mass
these
of
numbers that
approximately
we're seeing.
0 U's. It's actually
Loren, well, how about
1
15, 16,
2000
17?
Or so.
At this
And the neutron
point,
is about
300
1
tons of
U.
contaminated water is pouring into the Pacific
So zero,
Ocean
so
from
1 plus
Fukushima
0,
every
1 U
single
plus 0
day.
U's
And that's
equals
because
1 U.
Japan is an island arc. The nuclear plants are built on the coastline so they can use seawater,
Math, at
huge
least
amounts of
surface,
water every day
you can see
to
that.
cool the reactors. And the
Instant
runoff from the
But here's the conversion.
volcanic
1 U is
spine of Japan is
1.660
running
times
right
10
down
to
to
the
the
negative
coastline,
27
and it's
kilograms. How
washing
many significant
straight through
digits are in that?
Fukushima in that location,
in
and
this.
just carrying, it's a constant river of radioactive water washing into the
1,
sea.
2, 3,
Number
4.
16, a senior researcher
You
of
see that- you
marine
see that zero
chemistry
sitting out
at the
there to
Japan
the right
Meteorological
of the decimal?
Agency's Meteorological
It's
Research
the-
Institute
it means that
says
we
that,
know-
quote,
It-
30
it's much longer. I
billion
mean,
becquerels of
the,
radioactive cesium and 30 billion
accuracy
becquerels of
on these
radioactive
numbers is
strontium are
it's
being
out into
released
the teens,
into
even
the
20
Pacific
days.
Ocean
This
from
is what
Fukushima every
particle
single
physics
day,
is.
and I bet it's a lot more than that.
Dude,
Number
I don't know.
17,
Recalculate.
according to
recalculate
TEPCO, a
the
total
actual
of
physical
somewhere
masses.
between 20 trillion and 40 trillion becquerels of radioactive
National
tritium.
Institute of Science and Technology,
Radioactive
and there's a
tritium
little
is,
office, which is called
it's,
the Office of Mass
it's
Force.
radioactive water, basically, have gotten into the Pacific Ocean since the Fukushima disaster
There's a
first
couple. There's one in
began.
Boulder, which
Christina,
I
18, 19,
visited,
20.
also pretty cool. There's also one
According
there
to a
in,
professor at Tokyo
Rockville,
University, 3
And they had a lot of
gigabecquerels of
records
cesium
from
137
Twin
are
Towers,
flowing
like,
into the
in
port
the
at
area.
Fukushima Daiichi every single day. Again, that's just
Okay,
one isotope.
so this is
It's
mass.
just cesium-137. Number 19, it's
And
been
this is
estimated
energy.
that up to 100 times as much nuclear radiation has been
1
released into the
electron
ocean from
volt
Fukushima than was
is the
released
same
during the
as
entire Chernobyl disaster. Loren
602
just covered that
times
when she
10 to the minus
talked about
19
Chris Busby's
joules.
air filter studies.
So right here, you say, well, what
That's
does
underestimation.
a proton weigh?
Yeah.
Well, it weighs about 1.66 times 10
20
to
is one recent
minus
study concluded that a
27
very large
kilojoules.
plume of
How
cesium-137
much
from the
energy does an
Fukushima
electron
disaster
have?
will start flowing into
This is
U.S.
basically
coastal
the
waters
amount of energy
early
that it
next
would
year.
take if you wanted to go
Ocean
in
simulations showed the plume
and
of
pull
radioactive
a
cesium
single
released by the
electron
Fukushima
away
disaster
from
could
its
begin
atom.
flowing into the
It
U.S.
takes you that
coastal
much
waters
energy.
starting
It's just not
early
much.
2014
But
and
this is
peak in
happening
2016.
constantly.
Again, there's so many
throughout our
unknowns.
bodies. Like, for example, your
It's,
stomach acid.
it's
like,
going to
proton-
it's going to kill the
proton
ocean. It
pulses,
absolutely
squirting
is the
protons
coastline.
back and forth across membranes.
Lorraine,
so
go
that
to
the pH of your
21 and
stomach
22.
can maintain.
Okay,
Every time that happens,
21,
it's
it
about
is
this much
being
energy.
projected
So it's
that
about the same
significant
amount of
levels of
energy as that
cesium-137
single,
will reach every
proton
corner
did.
of the Pacific
But, you know,
Ocean by the
do
year
enough times,
2020.
it adds up.
That's because
Okay.
the ocean is very dynamic,
Einstein's
and that stuff
James
is
equation.
spread all over very rapidly, but not as rapidly as in the atmosphere.
E equals MC squared.
22
And
is
what this does,
being projected that the
this is a
entire
bridge
Pacific Ocean will soon
between
have cesium levels
Mass
5
and
to
energy.
10 times higher
So
than
it's-
what we
it's
witnessed
the
during
bridge
the
of the
era of
first law.
heavy atomic
It
bomb
actually
testing
says
in the
that
Pacific many decades ago.
the energy
That's
measured in
going
joules
to absolutely kill the fish populations.
Christina,
equals-
23, 24.
The mass
The immense
measured in
amounts of nuclear
kilograms.
radiation getting into the water in the Pacific has caused
Multiplied by the
environmental
speed of light
activist Joe
squared.
Martino
Again, there's
to
mass,
issue the
there's
following
squared
warning:
over
your
time
days
squared,
of
and
eating
we know
Pacific Ocean
that
fish are
equals
over.
Energy.
Mine were over 2
here's,
years ago.
Here's the speed of light.
Smart. You were ahead of the curve.
3 times
24 is the
10
iodine
to the 8
131,
meters per
cesium
second.
137, and strontium
we
90
need to do
that are
a,
constantly coming from Fukushima are going to affect the health
little
of those living
calculation.
in the Northern Hemisphere for a
really
very,
know
very long
how
time.
much
Just consider
energy
what
is
Harvey
going to
Wasserman
a
had to say
nuclear
about
power
this.
plant. And again, go back
Iodine
here.
131, for example, can be ingested into the thyroid where
all
it
the way
emits
back
beta
here.
particles
How much
that
energy is
damage
that?
tissue.
You could actually
A plague of damaged
calculate
thyroids has already been
exactly how much
reported by
mass
as many as
is
40% of the
missing.
children in the Fukushima area.
You know, so-
That
so fuel
percentage can
comes
only
in,
go higher.
it just
In
gets- it
developing
gets
youngsters,
turned
it
into
can stunt
pure
both
energy.
physical
And
and mental
the fuel coming
growth.
out,
Among
it
adults, it
weighs
causes
less.
a wide variety, a wide range of
Kinda like a campfire,
ancillary ailments, including cancer. Cesium-137 has been found in fish caught as far away as California. It spreads throughout the body, tends to accumulate in the muscles. Strontium-90's half-life is around 29 years. It mimics calcium and goes to our bones.
From matter
Loran
into-
25 and 26.
25, according
There's a
to
lot
a
of moisture
recent
content.
Planet
Again, look at the
InfoWars
water,
report, the California coastline
so
is
the
being
oxygen-
transformed into a
the
dead
oxygen out
zone.
of the
The California coastline is becoming like a dead zone.
in combustion.
And
in this,
if you
though,
go
the
to the
fuel is
beach,
just- it's just
you will see
there.
that the
The
rocks
fuel
are
is there
unnaturally
decaying. You
clean.
don't-
There's
you don't
hardly
add
any
air, you don't add
kelp,
water,
barnacles,
just
sea urchins
stick it in a
Showing
Together.
all the
anymore.
microscopic forms of life.
Yes, and the tide pools are similarly
Tons of
devoid
energy.
of crab, snails, and other scurrying signs of life. In other
It's creepy,
words,
isn't it?
these filter feeders that are taking in very high levels and bioconcentrating them are just
really
not
believe
able
it,
to
but it's
survive.
true.
And especially compared to
down
10 to
the
15
numbers.
years ago,
The,
when, you had to wear
500
tennis shoes if you
exajoules?
went to the beach, or you'd cut the heck out of the bottom of your feet.
Next week, 500 exajoules
Life is
per
being
year
exterminated. The ocean is going extinct.
20,000
Unbelievable.
And then it's carried into the
Hiroshima
Atlantic
bombs.
Ocean, and it will happen there, in the Arctic Ocean, and around the
per
Antarctic.
day.
They're killing the entire
Yeah.
global oceans.
26.
It is.
26
So
is a
this is
study
our-
conducted
this is our
last
annual
year came to the conclusion that
terrestrial
radiation from the
technological
Fukushima
energy
disaster
project.
could negatively
It's the same
affect
as blowing
human
off
life along the
20,000
west coast of North America,
atomic bombs
from Mexico
every
to
day.
Alaska for decades.
Loran 27.
It's contained.
According to the
Yes,
Wall Street
it's in the
Journal,
nu-
it's being
and this is-
projected
this
that
is-
the
it's in
cleanup
nuclear
of
reactor, it's
Fukushima
in the coal-fired
could take
power
up to
plants,
40
in the
years
gas
to
reactor,
complete.
It's in the solar
It's
panels,
never
in the wind
going to
turbine.
stop releasing in our
I
lifetimes.
agree. 28, Christina.
Yale professor Charles Perrow is warning that if the cleanup of Fukushima is not handled with 100% precision, that humanity
Yeah.
could be threatened
and
for
obviously- yeah,
thousands
and obviously
of
this is
years. And he is
Uncontrolled.
referring
This
to
is
the
controlled. So
fuel
like,
extraction,
You probably heard the gasoline
in part,
line that
which
blew
is
in
scheduled
Alabama
to
this
start
morning,
in
right?
15
Provides
days
1/3 of
from
the
reactor
Eastern
4.
Seaboard's
They actually are
transportation fuel.
currently
Shut down for a couple
moving the
weeks,
fuel
probably.
from
Cut-
reactor 6 into
Controlled.
the common spent fuel pool.
Uncontrolled.
Now, they began that in mid-October,
Well, there's no-
but it took
there's
them
no shortage
3
of
weeks
energy.
just to
There's
pry
always
off the
shortage.
reactor lid
All right, let's
in
take a
reactor
break and do
6,
some
and that
science.
reactor was supposed to be fine. It didn't have any damage that was reported. In